So welcome to this series on electrical machines. This is a two-part series, and that will be covered across 2 semesters. And you will be looking at 4 different types of machines in a broader sense. You will be looking at their principle of operation, their construction, their design, their characteristics, and some more in detailed analysis of these different machines. In a broader sense speaking, there are actually uh, 3 types of machines, electrical machines. You have the generators, you have electrical motors, and you have transformers. So, uh, generators, motors, and transformers, they deal with the transfer or conversion of electrical energy. As far as the generators go, uh, you have the mechanical energy is converted into electrical energy. Mechanical energy that's actually obtained from different sources. Say, for example, in case of a hydel power plant, you have running water that actually drives the turbines, and this mechanical energy is actually converted into the electrical energy. So potential energy of the water, when placed at some height, ultimately is converted into electrical energy. And so, without assuming any loss of energy, you can convert all of this energy into electrical energy. Then you have motors. Again, motors, they actually convert electrical energy into useful mechanical energy. So you have electrical energy obtained from generators extra. This can be put to use by for different purposes at residential level, commercial level, or at industrial level. In case of your own, if we talk about residential applications, you have motors in electric fans, you have motors in water pumps, you have motors in washing machines. So different types of applications are there of motors. Industrial applications, there are a huge number of there is in case of industries, you have a lot of applications of electrical motors. uh, you have basically almost 45% of the electrical energy generated worldwide is consumed by motor drives only. So that is actually, you can actually imagine how much application areas are of motors. 45% of the total electrical energy generated worldwide is consumed by drives, electric motor drives. Uh, and thirdly, you have the transformers. Transformers do not deal with conversion of electrical energy, but they deal with transfer of electrical energy. So you can transfer electrical energy from one circuit to another circuit or to n number of circuits using transformers. And this transfer of electrical energy basically takes place at the same power level. That means the input power to the circuit A will be same as the output power of circuit B, but the voltage level and the current levels will be different. So actually, the power levels are same, but we can change the current and voltage level. So while maintaining the same amount of power at both ends of the circuit, of at two ends of the circuits, two different circuits or three different circuits, we can actually obtain different voltage and current levels. So in a broader sense, these are your machines, electrical machines, generators, motors and transformers. This is actually one set of classification we can make of electrical machines. Generators convert mechanical energy into electrical energy. Motors convert electrical energy into mechanical energy. And the transformers, they will be involved with transfer of electrical energy. That you can change the voltage. That means you can actually transfer electrical energy from one circuit to another circuit. This transfer will be at the same power level but at different voltage and current levels. Moving on, as far as generators go, you can have DC generators or you can have AC generators. Again, motors, you can have DC motors and AC motors. So in case of DC generators, you are converting the mechanical energy into an electrical energy, and this electrical energy will be in the form of a DC voltage supply. In case of AC generators, mechanical energy will be converted to electrical energy, and this electrical energy will be in the form of an AC voltage. DC motors, you will be using DC supply you will be using the DC supply as a source of electrical energy, and that will be converted into mechanical energy. In case of AC motors, you will be using AC supply as a source of electrical energy and converting that into mechanical energy, useful mechanical energy. As far as transformers go, they only work on AC. You do not have anything like DC transformers. Now, this is another set of classification you can make. You can say there are DC machines and AC machines. So among DC machines, you have the DC motor and the DC generator. Among AC machines, you have AC generator, AC motor, and the transformer, because transformers only work on AC. Again, then, talking about AC machines and DC machines, you have a number of types of AC machines. You can have induction machines, you can have synchronous machines, you have the transformers. So these are some of the AC machines that we'll be studying in this course. There are other types of AC machines as well. As far as DC machines go, you have DC motors and DC generators. You can have then subtypes of these. So you can say there are the subtypes of these DC machines are you have series DC machines, you have shunt DC machines, you have separately excited DC machines, you have compound DC machines. So each of the DC machines, series DC machine, there will be a series DC generator, there will be a series DC motor, there will be a shunt DC generator, there will be a shunt DC motor. You will have a separately excited DC motor, you will have a separately excited DC generator, you will have a compound DC motor, you have a compound DC generator. So these are different classifications of DC machines. There are other machines that also work on DC, but for us, for now, these are the different types of machines that will be covering in detail in this course on machines. Fine. As I said to you, it's a two-part course. In the first part, you'll be looking at DC machines and transformer. In the second part, you'll be looking at the induction machines and the synchronous machines. Again, induction machines, you will have induction generator, induction motor. You will have synchronous generator, you will have synchronous motor. So all in all, these different types of machines, you will be looking at the construction, fine, the design of these machines. You will be looking at the principle of operation, you will be looking at the equivalent circuit, how we can represent a physically existing machine. It's electrical, it will be having both the electrical part as well as the mechanical part, how we can represent that using equivalent circuits. You will be looking at different characteristics of these machines. Fine, like the speed torque characteristics, talking about motors, you have the speed torque characteristics, or talking about generators, you have the terminal characteristics, there is the VI characteristics. Then you will be looking at the open circuit characteristics, short circuit characteristics. You will be performing various. We'll be looking how we can perform various tests on these electrical machines. Fine, open circuit test, block rotor test, no load test. Fine, a number of tests can be performed on different types of machines for different purposes. We'll be looking at all those different types of tests. You'll be looking at the phasor diagrams. We'll be looking at the phasor diagrams of AC machines. As in case of DC, there's nothing like a phasor, so we'll be looking at phasor diagram of AC machines only. That's transformers, motors, the induction motors, induction machines, and the synchronous machines. So you have all these things that we'll be looking into. We'll be looking at into different equations that will be actually derived from the equivalent circuit of this of different types of machines. These will be the voltage equations, the EMF equations, and the speed equations, the torque equations, different types of equations, the characteristics, tests, phasor diagrams of AC machines. So all these details, all these things, and certain other relevant details for different types of machines, we'll study them one by one for all these different types of machines. So this is actually how your course content is framed. You will have to study the construction, the principle of operation, the equivalent circuit, the characteristics, the tests of different types of electrical machines, be it DC or AC machines, as well as you'll be looking at the phasor diagrams of AC machines. So before we start with the actual machine, the first machine that actually we'll be taking up in the next session or so will be the DC machine. But before we take up that, there are certain terminologies or certain principles that you have actually studied in your 11th and 12th class that you need to actually revise, and so I'll be just going through them. I'll be rushing through them so that you just get a hold of it. You actually revise those concepts. Okay, so basic terminologies and principles that These will be actually the electromagnetic principles that you have studied. These are some of the terminologies that you will come across in electrical machines. Again, most of these terminologies you have studied. Say for example, you have angular position, theta, fine. So corresponding to linear scale, you have distance. So angular position is corresponding to linear concept of distance. You have, in case of angular notions, you have the angular position. So it is basically simply the orientation or the angle at which certain object is oriented with respect to certain reference point. Fine. So when we'll be looking at different rotational machines, so since motors as well as generators, they are actually rotational devices, and the transformer, it's the only electrical machine that's actually static. Motors and different types of motors and different types of generators that you'll come across, all of them, they are rotational machines. So instead of having linear concept of motion, we'll be dealing with now the rotational motion and rotational laws of dynamic motion, dynamic laws that are actually governing the rotational motions. Fine. So you have angular position, simply the orientation or the angle at which a certain object is oriented. You have angular velocity, we'll be representing this by omega, simply the rate of change of angular position, that's d theta by dt. You will be having the angular acceleration, that's actually d square theta by dt square. Fine. So with rotational devices, you have rotational laws of motion that will be actually governing this, that will be used. You have torque. So again, its linear equivalent is force. So torque is actually the force that you apply to a system, but this is again corresponding to an rotational object. Fine. So if an object is actually rotating, it's when so if a if an object is actually rotating, it will experience certain amount of force. This force is in case of rotational dynamics, it is referred to as torque. So in case of linear motion, it's actually the force that actually causes acceleration, that actually causes the velocity to change. But in case of rotationary devices, it will be the torque that will be responsible for change in angular velocity, or that will be actually responsible for production of angular acceleration. So in other words, you can simply refer to this as a twisting force. Right? And that will actually cause acceleration of your rotary object. It is referred to by torque, and corresponding to a radius of the radius r of the rotary body. If you have the force F that's actually applied to this, torque is given by Rf sine theta, or simply equal to R cross F. So Newton's law of rotation, you basically know for a linear dynamics, F is equal to ma. So in case of rotary, for rotary objects, for rotational motion, for understanding the rotational motion, you will say torque is equal to J into acceleration, angular acceleration, where J is actually the moment of inertia. Fine, and torque is the net applied torque. It's given in terms of Newton meters, and here the moment of inertia actually serves the same purpose as that of a mass in case of linear dynamic, in case of dynamics of a linear motion. Right. Work done. Work is given by integral of F in case of FDR in case of linear motion. Here it will be integral of tau d theta. Fine. So you can simply say it's equal to tau into theta. Similarly, power. Power is given by rate of change of work. So you can simply say if this is tau theta, this will be given by d, and this will be given by d by dt of tau theta. Fine. So if assuming tau is constant, d by dt of theta, d by d theta by dt is nothing but your angular velocity. So this is equal to tau omega. So this is one important equation that you'll have to remember. P is equal to tau omega. So we will be using this equation a lot in case of electrical machines. The power equation, how to derive the power at the shaft of the rotary body. Power is equal to tau into omega, where tau is the net applied torque and omega is the angular velocity of the body. So these are different terms that you will come across while studying electrical machines. You have most of these terms you have actually are familiar with. Then there come the principle of the electromagnetic principles. There are three principles. The first principle is if you have a conductor that is placed in a magnetic field, fine. You have a conductor of length L and this is placed in a magnetic field and it's carrying current I. So this particular conductor will actually experience force, and as we have said, in case of and this is actually the principle of operation of a motor. You have a conductor that's carrying current I placed in a magnetic field. It will experience force. This force will be given by for a linear motion we can say this force is equal to I L cross B, or you can say I ILB sine theta. So this is for a motor when a conductor is placed, when a conductor of length L carrying current I is placed in a magnetic field, it will experience force, or you can say it will actually experience a torque. We'll be actually equating this force into later into torque. So this torque will be equal to ILB sine theta. This force that actually this conductor experiences. This is the principle of operation of a motor. This is actually the principle of operation of a linear motor. The basic principle of electromagnetic given by uh, secondly, mm, you have a conductor again placed in a magnetic field, and a conductor of length L is placed in a magnetic field of intensity B, and this conductor is actually rotating. Fine, it's not carrying current now. So you have a rotating conductor placed in a magnetic field. So EMF is induced in this conductor. So the induced EMF in this is equal to V cross B dot L, where V is actually the velocity with which this conductor is actually rotating. Fine. So again, you can equate this to you can find out the angle between V and B, and you can find out the angle between V cross B and L. This is the principle of operation of a generator. So as per this electromagnetic principle, if a conductor of is rotating in a magnetic field, so an EMF is induced in this conductor, and that's the principle of operation of a generator. The third principle given by Faraday is basically involves with time rate of change of flux. So as per this principle, if a voltage will be actually induced in a circuit, that's actually associated with changing flux. Fine. So you have, say for example, wire, and a flux is actually there's actually flux moving through this wire, and that flux is actually changing with time. Therefore voltage will be induced in this coil, and this voltage will be equal to d phi by dt. Fine. And it will be actually negative as per the Lenz's law. So if you have n number of coils, for n number of coils, or n number of turns of this coil, uh, and turns of this coil rather, the EMF induced will be equal to minus n d phi by dt. So yeah, so there is a coil, and that's actually through which flux is changing with respect to time. We'll be actually seeing how this is associated with the changing flux. So if a changing flux is moving through a coil, EMF will be induced through that coil. Fine. So if this flux were not changing, it were constant, in that case the EMF induced would be 0. So this forms the principle of operation of a transformer. So you need to remember these three principles of electromagnetic, these three electromagnetic principles. One, a conductor a current carrying conductor when placed in a magnetic field will experience a torque, will experience a force. That forms the principle of operation of a motor. Secondly, conductor, when moving in a magnetic field, it will an EMF will be induced in that conductor. Thirdly, a coil that's actually stationary at any location, but through which flux is changing. It's associated with changing flux. So because of that changing flux, EMF will be induced in this coil. It can be one turn of coil, it can be n number of turns of this coil. So accordingly, you will get the induced voltage. So this forms the principle of operation of a transformer. So you need to remember the basic terminologies associated with rotational motion. You need to remember these different principles of operation. These will actually form the basics of any machine. Apart from this, you need to remember different types of losses associated with the machine. Copper loss, core loss. These are simply I square R losses. Fine. So if a current is your electrical circuit basically has a resistance and current is flowing through this, so the power dissipated in the form of heat through this through this material will be equal to I square R, and these are referred to as copper losses. Apart from this, you have the core losses. Core losses are actually composed of two different types of losses: the hysteresis losses and the eddy current losses. We'll be studying these hysteresis losses and eddy current losses in detail. And thirdly, you have what are you have other types of losses in the system. You can have frictional losses. You can have mechanical damper winding losses. You can have mechanical losses. You can have stray losses. You can have frictional losses, winding losses. So all these different types of losses will be associated with the machine. Frictional losses, winding losses, stray losses, other types of losses that are actually undefined. Fine. And you can have mechanical losses due to the rotational motion. So all these different types of losses will actually also come across in different types of machines. We'll actually study them in detail at a later stage. So this was just the basics of what we'll be covering in this course, and what are the different principles that you need to remember, that you need to revise. Actually, basic terminologies that are actually associated with the rotational motions that you need to revise. And we will also be concerned with different types of losses in different machines. We'll be looking into the details of these different types of losses. For every type of machine, it will vary, and there will be certain factors that will be governing the intensity of these losses. We'll be looking into that. So that's actually for today. That actually is for this session. We'll be starting with the basics of a rotating machine in the next session.